So this is the third video for this lesson. None of these are too long, so hopefully they're manageable. You've just watched a video by Jeff Phillips that I think does a really nice job visualizing this kind of complicated definition for entropy, that we're actually counting the number of possible microstates of a substance, where the microstate is a certain distribution or arrangement of matter and energy. So a few more details that we can put into this definition. If you have a solid material, a perfect crystal at absolute zero, 0 degrees Kelvin, by definition, that has an entropy of zero, S equals zero. This is actually the third law of thermodynamics. But as we increase temperature, there's more energy there, and there's more molecular motion. Even as we increase the temperature of a solid, that solid is vibrating more. And then, of course, when it melts and becomes a liquid, we've got much more molecular motion. So you can kind of imagine that as motion and energy increases, there's just more ways to arrange energy and matter. So yeah, on this graph here, temperature change is causing the dispersal of energy on the y-axis, and phase changes are causing the dispersal of matter on the x-axis. So as we kind of stair step or even just go up at a diagonal, we're increasing total entropy. So a couple of things we can draw from this. For any given substance, the entropy of the gas phase is going to be greater than the liquid, which is going to be greater than the solid. And then also even within a phase, there's also going to be an increase in entropy with an increase in temperature. This graph shows for a particular substance the actual entropy at each temperature. And so you can see that, yeah, the entropy is increasing with temperature, but relatively slowly within a phase. Then there's a big jump up with a phase change. Slow increase as within the liquid phase, and then a big jump up, much bigger than that previous jump, to go from a liquid to a gas, because those particles can be so much more easily dispersed. Let's look at some real data, and let's also introduce a quantity called standard molar entropy. This is a state function, meaning that or entropy, I should say, is a state function, meaning that it is really only dependent on the conditions of the substance, not the path it took to get there. So entropies are for particular temperatures. This is standard temperature, 298 Kelvin. And yeah, we represent the standard molar entropy. We put that little degree sign there to indicate that standard state. And yeah, these values can be looked up. There's a good table in your text, table 16.1, that has a much longer list than what you see here. And the units on entropy are joules per mole Kelvin. So I want you guys to take a look at this list that we see in front of us, and see if you see any patterns. We go from solids to liquids to gases on this table. Anything you guys see? Pause it for a second and maybe jot down some notes on what you see here. Yeah, I would say that even when we're comparing different substances, gases have a greater entropy than liquids, which are greater than solids. That's not true across the board. Like, for example, if we compare bromine down here, which is a liquid at 298 Kelvin, it has a higher entropy than helium gas, at the same temperature. Also, another trend I'd like to point out is that among substances of a similar structure, similar molecular structure, for example, the hydrocarbons here, the entropy increases with increasing molar mass. And again, that's due to just, if there's more atoms, there's more ways to sort of, there's more different ways of orienting the atoms and the energy within the molecule, because all those atoms are moving around slightly and vibrating. So yeah, as the molecule becomes more complex, there's more ways for those atoms to move. Let's do a little bit of practice. So I've got a couple pairs of substances. Let's predict which has the larger standard entropy. So first, if we have 1 mole each of mercury versus gold. Again, maybe pause it and take a look at each of these 3 examples, and then come up with some answers and then press play to see what the answers are. So between mercury and gold, pretty similar elements. They're near each other in the periodic table, but gold is heavier. There's more matter there, there's more mass. So 1 mole, there's just more ways to distribute the energy if you're working with gold as opposed to mercury. Moving on to B, 1 mole each of nitrogen oxide or nitric oxide and nitrogen dioxide. So here we have two similar compounds. They're kind of in the same family. And so we would expect the heavier one, NO2, to have the higher standard entropy. Now the third one here is maybe a little trickier. 2 moles of NO2 compared with 1 mole of N2O4. Now, if you're thinking, you're saying, well, if I have 2 moles of NO2, that's the same total number of atoms as 1 mole of N2O4. But let's think about these two things. So with NO2, if we've got 2 moles, that's twice as many particles, and these are both gases, as the N2O4. There's a lot more movement there, a lot more potential for dispersal with those NO2 molecules. And let's take a look at the actual values for these last two examples. So we can see that NO2 is greater than NO. And now comparing NO2 and N2O4, on a per mole basis, N2O4 has a higher entropy. But if we are looking at different amounts, since these are per mole, if we have 2 moles of NO2, we will multiply that quantity times 2 to get that total amount of entropy, because the more molecules we have there, again, just the more potential for dispersal there is. So multiplying standard molar entropy by the number of moles would give us the total amount of entropy there, and it would be greater than 1 mole of N2O4. So now that we've quantified how entropy can vary between substances or between phases, let's think about it in the context of a reaction where bonds are being formed and broken. Entropy will almost always change during a reaction. Again, bonds are breaking and forming, phases might be changing, molecules are rearranging, there's a lot going on. And if a reaction is occurring under standard conditions, we can use some of those tabulated values that we just saw to predict the entropy change of the reaction itself. We can look at the entropy of all the reactants before the reaction and the entropies of all the products after the reaction to get the change in entropy over the course of the reaction. We do this in a very similar way to how we calculate enthalpy of formation, which goes back to last semester. And this equation here, which always looks really complex, is really just telling us that we're going to sum up the entropies of the products and then subtract the entropies of the reactants. We're going to have to consider, each reactant, each product, and how many moles are involved. But really, we're just kind of adding things up and looking at the difference to get that change over the course of the reaction. So next up, I'll do an example on paper for you guys to follow along with. Before I hop to the paper, let me just show you guys the molecules, the structures for each of the reactants and products in this reaction, and give just a little bit more background. Yeah, we're looking at the production of acrylonitrile, and it's formed from 3 gases, propane, ammonia, and oxygen. It forms these 2 products, acrylonitrile and water, which under the conditions of this reaction are liquids. Over here is the data that you can look up from a table. You can Google it, but the standard molar entropy for each of those things. One thing you want to be really careful of is many substances can exist as a gas or a liquid or a solid and a liquid depending on the temperature. You want to make sure you get the entropy for the correct state of matter. So water has a much higher entropy if it's in the gaseous phase. So that's just one little tip before I jump into the pen and paper exercise.
Okay, so I have a reaction here. This is for the formation of acrylonitrile, which is a starting material for some synthetic fibers. It's made from the gas propene, C3H6, as well as ammonia and oxygen. So if we're trying to find the entropy, the reaction entropy for this particular reaction, we're trying to figure out if over the course of the reaction, things are getting more dispersed or less dispersed. And it's good to kind of take a look at it before you actually start throwing numbers onto here. We're starting out with 3 gases, right? And the products of our reaction are 2 liquids. So right off the bat, we can probably take a guess that the reactants have a higher entropy, a higher state of dispersal than the products. And since our reaction entropy change is the sum of the products minus the sum of the reactants, we are probably going to be looking at a negative value here. So whenever I start a problem like this, I'm going to write down my reaction. Even if I have a paper in front of me, I'm usually still going to write it down. And oftentimes the data might be given to you in a table. I make a lot of mistakes, so I'm going to go ahead and write those values right under each reactant and product so that I don't, mix anything up. So the propene has an entropy value, standard molar entropy of 227 joules per mole Kelvin. The ammonia is 193. The oxygen is 205. And then on the reactant side, or the product side, I've got 188 and 70. So yeah, let's go ahead and start to solve for this. So I'll rewrite the formula I'm going to use here. My entropy change for the reaction is the sum of the products entropies times each coefficient. I'm going to add all those guys up. And then I'm going to subtract the same quantity for the reactant side. So I'm going to take each of the 3 reactants, multiply the coefficients, times the standard molar enthalpies. So yeah, let's go ahead and do that. So for my products, these 2 guys over here, I'm going to have 2 times 188 plus 6 times 70. So that gives me a total of 769. On the reactant side, I'm going to have 2 times 227 plus 2 times 193 plus 3 times 205. And that's going to give me a total of 1,455. So yeah, my change in entropy over the reaction is 769 minus 1,455 for a total of negative 686 joules per mole Kelvin. So yeah, as I suspected, my reaction, because of that negative sign there, what that symbolizes is that entropy is decreasing. This is my change in entropy. So if it's negative, that means it's decreasing. I think it's also useful to think about this in terms of dispersal. The negative is almost like a double negative here because we're getting, if entropy is dispersal, we're getting less dispersed, or disordered is another way to think of it. And so the opposite of that is that it's getting more orderly or more ordered. So that's what a negative delta S of reaction tells you.